Hi, my name is MJ, and this is my Summer of Math Exposition 2 submission. Today, I will explain an interesting generalization of the cross product to higher dimensions using objects I call crossers, and investigate some of their properties. Don't worry, knowledge of the cross product is not required to understand this video, and I'll put links in the description. Before we get into the main topic, I should note that this video will use the language of geometric algebra, a near-universal notation which can be used to formulate the complex numbers, quaternions, octonions, and vector algebra. A full review of geometric algebra would take quite a long time, but for the purposes of this video, all you have to understand is the geometric product. First, we denote unit vectors using the letter E with a hat and a positive integer subscript, and we define the geometric product for unit vectors as EI EJ equals EI dot EJ plus EI wedge EJ. Here, the dot product is non-zero with a value of 1 if and only if I and j are equal, and the wedge product is non-zero with a so-called bivector value of EI EJ equals minus EJ EI if and only if I and j are different. This object, EI-EJ, is equal to minus EJ-EI because we define the algebra of these unit vectors to behave this way. That is, we define the wedge product to be antisymmetric. And yes, I understand that seeing unit vectors multiplied by one another can look strange at first. But if you can get past that initial bit of discomfort, you will see how powerful of a tool geometric algebra is. Here are two examples of the geometric product in action. The first one is the geometric product of two vectors in 3 dimensions. You can see that by first distributing, then applying the rules of the geometric product for individual unit vectors and combining like terms, we find an example of the general fact that the geometric product of two vectors can only have non-zero scalar and bivector parts, that is, cannot contain vector terms, trivector terms, and terms which are wedge products of 4 or more unit vectors. In fact, the number of unit vectors wedged together is called the grade of the object in question. Said in this language, the geometric product of two pure vectors of grade 1 can only contain grade 0 and grade 2 terms. In this second example, we see that the geometric product of a bivector with a trivector can produce multiple kinds of terms. For the purposes of this video, we will only care about the terms which use the smallest amount of vectors coming from products like these, the terms of the smallest grade, which we will call the dot product, in analogy with the dot product for vectors. Other generalizations of the dot product do exist, but they aren't necessary to introduce here. And that's it. If you understand the very basics of the geometric product now, the rest of the video won't require a lot more outside knowledge. So now that we've seen all this machinery, what can we do with it? Well, we can discuss the cross product in 3 dimensions. Remember those two 3D vectors from before? Instead of calculating their geometric product, let's calculate, up to a sign, a unique vector which is perpendicular to the original 2. Some might argue that this is a more natural sense of multiplication, because when we multiply real or complex numbers, we get real or complex numbers of the respective results. How might we get a vector back when we multiply two vectors? In 3 dimensions, assigning a unique vector to any pair of two vectors turns out to be an easy game, so let's play with the basis vectors to get a sense of what that means. If I give you E1 and E2, you can give me E3. If I give you E2 and E3, you can give me E1, and so on. Since there are only 3 objects, it's obvious which vector to give me if I give you the 2 others. In the language of geometric algebra, this process amounts to first taking the wedge product of my 2 vectors, then taking the dot product of the resulting object with the trivector E1, E2, E3, called the pseudoscalar in 3 dimensions, as it is the highest grade object available up to scaling. So, you might ask whether this process can be used to assign a unique vector to any pair of vectors in the space of dimension D, and the answer is no. For example, take 4 dimensions and the exact same vectors we just used. Their wedge product remains the same, but now taking the dot product with the object E1, E2, E3, E4, the 4D pseudoscalar yields a bivector, not a vector. One can see how multiplying 2 vectors and choosing the complement in the space in question does not produce another vector in general. One natural question to ask here is when exactly one can make such unique assignments, and we'll get to that. But first, it will be interesting to look at another example, the cross product in 7 dimensions. In 7 dimensions, the wedge product of 2 vectors still contains only a bivector part, but dotting with the pseudoscalar then yields a grade 5 object, not a grade 1 object as we would like. How can we make an object which, when dotted with the wedge product of our 2 starting vectors, uniquely yields a 3rd vector? One way is to somehow write down a sum of terms, each of which is the wedge product of 3 vectors. For example, we can choose E1, E2, E3, plus E1, E4, E5, plus E1, E6, E7, plus E2, E4, E6, plus E2, E5, E7, plus E3, E4, E7, plus E3, E5, E6. This object, which I call a crosser, mimics the 3D cross product in 7 dimensions. If If we play an analogy of our game from before using this new object, if I give you E1 and E2, you know to give me E3. If I give you E1 and E6, you know to give me E7, and so on. Dotting the wedge product of two vectors with this object therefore uniquely determines a vector from the first two. However, the definition of this object is not unique, as switching any two unit vectors, E1 and E2 per se, yields another equally valid choice. However, let's ignore such permutations for the purpose of this video. One interesting thing to do is compare the 7-dimensional cross product with the original 3-dimensional one. 3D case obeys associativity under multiplication, that is, A times B times C equals A times B times C, and up to a minus sign is identical to quaternion multiplication. Looking to the 7D case, we see that it does not obey such associativity, and it is in fact identical to the octonions up to a minus sign. What happened? In the 3D case, there was no decision to be made. By dotting the wedge product of the two vectors in question with a pseudoscalar, a unique vector orthogonal to the first two can be found. But in 7D, a choice had to be made about the permutation of the unit vectors in the crosser. This choice amounts to projecting the geometric product of the two vectors being multiplied onto a set of 3D subspaces and then summing the complements of each of those projections to generate a vector. So, one natural question to follow up with is how we can construct crossers in other dimensions. To figure out what that would even mean, we can examine this crosser's properties. Firstly, it is in 7 dimensions, so let's call d equals 7. Secondly, it involves 7 terms, each of which is a wedge product of a set of unit vectors, so let's call that s equals 7 for the number of sets. Each set of unit vectors contains 3 unit vectors, so let's call that number n equals 3. And each unit vector is used 3 times in total, so let's call that u equals 3. One thing to notice is that these quantities are interrelated, as s times n equals u times d, which must be the case because the number of sets of unit vectors multiplied by the number of unit vectors in each set must equal the total number of elements used in all of the sets, which must equal the number of unit vectors used multiplied by the number of times each one is used. A fifth quantity we can define as O, the number of unit vectors shared by any pair of sets. For example, choose any two of the 7 terms used, and you can see that they share exactly 1 unit vector. But in the case of the 3D cross product, we see that d equals 3, s equals 1, n equals 3, u equals 1, and O is undefined, as there is only one set, and therefore it doesn't make sense to talk about the overlap between distinct sets. Here's another example of a crosser in 6 dimensions this time. E1, E2, E3, plus E1, E4, E5, plus E2, E4, E6, plus E3, E5, E6. D equals 6, s equals 4, n equals 3, u equals 2, and O equals 1. This crosser doesn't fulfill all of the nice properties we might like when used to multiply vectors. For example, there's no term in which E1 and E6 are present, so the product of E1 and E6 using this definition of a 6D cross product is 0. However, this example and the others provided before suggest the question, how is O related to S, N, U, and D? Phrased another way, how can one tell whether or not the tuple S, N, U, D, O corresponds to a valid crosser or not? Before showing how we might answer that question, it's worth stepping back and considering that because we have defined the variable n to describe the number of unit vectors in each term of the crosser, we are being more general than we need to be in order to describe multiplication of 2 vectors to yield the third, but that's okay. This is just an interesting problem in its own right, and we can always specialize to n equals 3 again if we like. After a bit of playing around trying to solve this problem, one might think to write each set corresponding to a term in a given crosser not as the wedge of the n unit vectors involved, but rather as the sum of them. This may seem a little strange because the terms being summed to construct a crosser are in general not vectors, which is the case only when n equals 1. But the idea of writing objects one is interested in as vectors is actually a widely used technique, and as long as we know that these vectors are auxiliary tools, there's no problem with using them. For example, using vector notation, we see that our 6D crosser may be represented as the following 4 vectors. Call these vectors the crosser vectors. Why is this useful? Well, we can translate the properties of our crosser into a set of properties of these vectors. Firstly, the crosser vectors all have the magnitude square root of n, as one can quickly check. Secondly, they all point to the corners of a 6D unit hypercube living entirely in the 6D analogy of the first quadrant, or octant. Thirdly, the angle between any two crosser vectors is the arc cosine of O over n, using the well-known formula of calculating angles between vectors. Links in the description. Fourth, the sum over all the entries of each crosser vector is n, meaning that they all point to points, which we will call crosser points, in the plane x1 plus x2 all the way up to xd equals n. The distance between this plane and the origin is n over the square root of d, as one can see with a little algebra. An intuitive way to calculate this distance is to notice that because all the vectors have the same magnitude and correspond to points living in this hyperplane, the hyperplane must be orthogonal complement of the vector 1, 1, 1, blah, blah, blah. In other words, there must be some vector proportional to that vector, which can be subtracted from each crosser vector derived from the crosser in question to yield a set of vectors living in a hyperplane parallel to the first, but containing the origin. A bit of playing around will show you that this vector is n over d times 1, 1, 1, 1, blah, 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 whose magnitude is n over square root of d. With this vector as a leg and any crosser vector as the hypotenuse, we can then construct a right triangle. It is right because by being the orthogonal vector from the origin to the hyperplane in which the tips of the crosser vectors live, this orthogonal vector is the projection of any crosser vector onto the subspace orthogonal to the hyperplane. Using the Pythagorean theorem, we can find that the magnitude of the third side of the triangle, the one in the hyperplane, has length square root of n minus n squared over d. Because this approach has not relied on us choosing a specific crosser vector, we know that all of the crosser points are this distance away from the point n over d, 1, 1, 1, 1, and so on. We also know that since the angle between the two crosser vectors is the same, the distances between the crosser points must also be the same, as all of the crosser vectors have the same magnitude. This means that the crosser points form a regular simplex, which is a generalized version of an equilateral triangle or a regular tetrahedron. Having calculated the distance from the center of the simplex, which is pointed to by the vector orthogonal to the hyperplane in which the crosser points live, we have actually calculated the circumradius of the regular simplex. We can relate this distance to the side length of the simplex by dividing by a factor which I won't derive here, but which is the ratio of the regular simplex's side length to its circumradius as a function of the number of points used to form the simplex. I will leave a link in the description to a derivation of this result, but for now, let's just multiply our result by the square root of 2s over s minus 1 to arrive at the side length of our simplex. Now let's calculate the side length of the simplex directly without using the circumradius. We can form an isosceles triangle where the two equal length sides are any two crosser vectors, and the third side will be an edge of the simplex. We know that the angle between any two crosser vectors is theta equals arc cos of O over n. We can therefore express the side length of the simplex as the square root of 2 times the square root of n minus O. Setting this equal to the previous expression, also equal to the side length of the simplex, we find a relationship between O, n, d, and s. In solving for O, we find that O equals n multiplied by u minus 1 divided by s minus 1. A few points. Given a tuple which obeys this relation, one can always find new solutions by scaling n, d, and o by the same integer value, call it k, and find a new valid tuple. Also, there is always a dual tuple which satisfies s prime equals s, n prime equals d minus n, u prime equals s minus u, d prime equals d, and o prime equals d minus 2n plus o, which is a solution if and only if the original tuple from which it is derived is a solution. If you're interested in generating some tuples yourself and seeing a matrix or geometric algebraic representation of them, I've left some Python code below. You can also use the code to multiply different objects using the generated corresponding crossers. Just a small note, the geometric algebraic aspect of the Python code relies on the Clifford package, which is also linked in the description. Thanks so much for watching, and have a nice day.